So today what we're going to do is go over section 3.1. This is about the derivative of polynomials. There's also supposed to be an additional part about the derivatives of exponential functions, but we'll leave it until the end of the chapter. So as you know, we have been doing differentiation for a while now. And what we have been doing is using the difference quotient. So if you don't remember, the difference quotient looks like this. So given some f of x, so f of x is a function, then its derivative, f prime of x, is equal to the limit as h approaches 0. And then we have f of x plus h minus f of x. And then, of course, that's going to be all over h. So the idea here is starting now is that we don't want to have to use the difference quotient to find a derivative every time because that takes a bit too long for what we're trying to do. So what we're going to do is we're going to establish some differentiation rules, and that's the focus for this entire chapter. And you can think about them as shortcuts of what we're trying to do. So it is a skill, so you will need some practice in order to be good at it. And we will be providing you with enough of that practice and be answering questions as you have them. So today is just going to be on polynomials. And we're going to start with the most basic one. So if you have some f of x, which is a constant, and that constant is a real number, think about what happens. Well, we have a function that is just c. So this will be the function. It's just going to be a horizontal line. And of course, the y-intercept is c. Now, this number could be anywhere. It could be above, below, who knows. But what you will notice is that the slope everywhere along this line is 0. So be it the tangent or the secant slope, you're going to have a slope of 0. So then the f prime of x, given that f of x is just a constant, you're going to have 0 as a result. And you can prove this pretty easily using the difference quotient. So imagine if you were to use the difference quotient in this case. So you have h approaches 0. You're looking for that limit. So you're going to have, in this case, c minus c, and then all over h. So really, it's going to be just 0 over h. Okay. So you can show pretty easily that that's what will happen. Oops, sorry. Let's fix that right now. You're going to have a number that is already 0 divided by a number that is approaching 0. So the limit should just be 0. Okay, so that's is the case. Now, the next piece is to see what we have if we have other powers. So let's say we have f of x equals x to the n power, where n is a real number, but we're just going to have some natural numbers here for now. We have x to the 1, 2, 3, 4, and 5. And using what we know, using the difference quotient, we can find the derivative to be 1, 2x, 3x squared, 4x cubed, and 5x to the 4th power, respectively. So we can generalize that result by saying that if f of x is x to the n power, then its derivative would be f prime of x, which is equal to n and then xn minus 1. So you can see that the exponent decreases by 1 every time we take the derivative here. And then the original exponent becomes the coefficient. Okay. And again, you can show this using the difference quotient, but we have done a few examples back in section 2.8, so we're not going to do more here. All right, so that means we can find derivatives of polynomials really easily now, which is kind of the goal. So if we have f of x equals to x to the sixth power, then the derivative would just be 6x to the fifth power. Likewise, here we have y prime equals to 1000, and then x to the 999. Now we have v, which is an unusual one. We're going to use a different notation here. We're going to write this as dv ds, which is equal to 3s squared. And finally, we are looking for the derivative in terms of r to the fourth power, and that will just be 4r cubed. So if you notice what we said about the rule in the previous page is that this works for real numbers. So n doesn't have to be a natural number, as it is the case here. You have 6, 1000, 3, and 4. Now this will also work if we have negative powers of x. So let's look at example 2 together. And you can see here, for example, we have f of x equals to 1 over x squared, which of course you know can be written as x to the negative 2 power. So its derivative would be negative 2 x to the negative 3, right? Because you are going to decrease the power from negative 2 to negative 3, and the exponent becomes the coefficient. So, and then you can rewrite this as you like as negative 2 all over x cubed. Okay, if you want the answer to look more like what the question looked like. And this will also work for even something like this, which is cube root of x squared. Of course, then you can rewrite this as x to the 2/3 power. Right, the numerator is the exponent and the denominator is the root. And here we're going to match it. So we're going to write y prime is equal to 2/3 x, and then 2/3 minus 1 is negative 1/3. So if you were to write everything out, you have 2, which is the numerator, all over 3, and then the third root or cube root of x. All right. Now, the next one we have x square root of x. And we actually can treat it as though it's the same as the previous two examples. What you're going to do is rewrite this as x to the first power, because you have an x, and then multiply by x to the 1/2 power, which of course is the square root. And now you can add the exponents together. We're going to have x to the 3/2. And then if you take the derivative of that, you're going to have simply 3 over 2 x to the 1/2. And of course, you can also rewrite x to the 1/2 as square root of x to write the answer more nicely. Something like that. All right. So far we haven't had any coefficients in front of our powers of x, we have x to the negative 2, x to the 2/3, x to the 3/2. And in the previous questions here, we also have no coefficients in any of these. So what we're going to do is introduce additional rules to make taking those derivatives easier. Let's say I want to take the derivative of, I don't know, 5x squared, right? So let's look at the rule itself first. It says if y is equal to c times f of x, where c is some real number, then the derivative is going to just be c times f prime of x. Okay, there's a couple of different ways to prove this, but we're going to use a different quotient for this case. So I'm going to start with y equals c and then f of x. So the derivative, of course, will be the limit as h approaches 0. And then you will have, of course, c, c, and then f of x plus h, then minus cf of x all over, oops, that's the wrong color. That's better. All over h. So what you'll realize is that you can factor out c, and then you can use the limit laws from chapter 2 to actually put the c in front of the entire limit. So you can have something like this. So it would just be left with f of x plus h minus f of x and then over h. Now, of course, this is just the derivative of f of x. Oops, sorry. Forgot a prime there. So yeah, the end result that you get will be c as a constant in front of the limit. And then inside the limit, you are going to be left with f prime of x. Okay. So next up, we have the sum in difference rule. It's pretty intuitive. You're going to use the same difference quotient proof if you like. But the derivative is just going to be y prime is equal to f prime of x and then plus or minus g prime of x. Okay, so I'm not going to do the proof here. It's pretty self-explanatory. Um, basically, it's just what I did earlier. And you can just use the adding and subtracting symbols to sort it all out. So it's not too difficult. So I'll leave it for you to figure out. I think it's also a homework question anyway. So, all right. So really quick, I just wanted to show you what happens if you apply these additional differentiation rules to what we already have. Starting with the first one, we have f of x equals 3 times x to the 4th power. Then its derivative will be, let's see, 3, and then we just take the derivative, that would be 4x cubed. And of course, then you can multiply the coefficients together to get 12x cubed. Here should be pretty obvious that the derivative is just going to be -1, right? You can kind of factor out the negative sign. The derivative of x is just 1, so you have -1. Now, a polynomial that you're more familiar with, so what would its derivative be? Well, the first term will give you 4x cubed. The second term, you will get a 3. So 3 times 10 is 30, of course, and then just x squared. derivative of x is just 1, so you have a 6, and then derivative of the constant term will be 0. So that's that one. Last one. Now later on in the chapter, you will learn how to take the derivatives of products, but for now we're not going to introduce that rule just yet because it is a bit different. What we're going to do instead, we're just going to multiply this out. So we'll have x root x minus root x, of course, if you distribute the root x inside the parentheses. And then you can rewrite this. We did something similar to x root x already. You know that this is x to the 3 halves. And then the second term, of course, is x to the 1 half. And we can take the derivative this way. So the first term will just be, see, equal to 3x, sorry, 3 over 2, and then x to the 1 half. So this would be, oh my goodness, the notation is a bit all over the place. Sorry about that. All right, so this is not the derivative just yet. This is the derivative down here. I just wanted to clean things up a little bit. And then if you take the derivative of the second term, the coefficient is 1 half, and then you have x to the negative 1 half power, because 1 half minus 1, of course, is negative 1 half. And you can fix everything into the square root form. So this would be 3 over 2 root x minus 1 over 2 root x. Okay. So this is a combination of the first rule for when we take the derivative of a single term, a monomial, right? So if you have x to the n, then its derivative would be n x to the n minus 1. And then we also have the sum and difference rule, right? So if you take the derivative of that, you get f prime of x plus g prime of x. So that's so example D is a combination of these two rules working together. Okay. So last one, we're going to combine these new differentiation rule to a question that you're more familiar with, and that is finding the equation of a tangent line. So we are going to start this one off by multiplying the square out. So we're going to write this as y equals to 1 plus 2x times 1 plus 2x, of course. So if you multiply that out, that will be equal to 1 plus 4x plus 4x squared. Okay. So if you were to take the derivative of this, where it is y prime, the derivative of 1 is 0, the derivative of 4x is just 4. And then the derivative of 4x squared is going to be 4 times 2, which is 8. And then the x squared becomes just x, right, because the power decreases by 1. So that would be the derivative. Of course, this is how you find the slope of tangent. So the next step, if you will, is to let x equals 1. Because once again, we're looking for the tangent line to the curve at 1, 9. So the x value there will be 1. So we're going to let x equals 1. So substitute it in. So y prime is equal to 4 plus 8 times 1, which is just 8, of course. So the slope of the tangent will be 12. And then finally, you are already given the point, so this next part is a little bit easier. And just gonna write it out. So we have the tangent line, of course, is y minus y1 is equal to m x minus x1. So in this case, y1, of course, is the 9 that's given. M is the slope of the tangent, which we know is 12. And then x minus x1, of course, that would be the 1 there. And then if you want to rearrange the terms, you will get y is equal to 12x minus 3. Okay? And that's more or less all the question types that you will see if it is just the derivatives of polynomials. Now we included things that are not polynomials per se because they wouldn't have rational powers, but since the rule works, we might as well introduce them now. And that's more or less it. So we can continue with more differentiation rules tomorrow. Thank you for listening.